Okay. All right. So this is left over from my previous class. We were talking about time complexity in my other class. Obviously, we're not going to do anything like that in this particular class. So that's kind of, you know, what we talked about in the previous class. In cisp310, not 440. All right. So are there any questions about the homework assignments? Because you guys have, I think including the one due today, you have 2 outstanding homework assignments. One is the swap subroutine, that's due tonight. And then the other one is Fibonacci, that's due on Thursday. So are there any questions regarding any one of those 2 homework assignments or subroutines in general? No questions about those? Any questions about the concepts? Yep, go ahead. Fibonacci? Okay. You mean the C code or? Okay, I can go over the C code because I used the ternary operator. Is that the question? Interpreting the ternary operator? Okay. All right, so if you're just talking about the ternary operator, we can look at this expression here. So we'll just say that x equals to some condition, and then we have a value a, and then the colon, and then the value b, okay? So this really means the same thing as if c, else. So if c is true, then x equals to a, otherwise x equals to b. That's basically how a ternary operator works. So in the homework assignment, okay, when you implement the Fibonacci recursive subroutine, you can do it kind of this way too. And a underscore t, this is n. So one way to do it is to do it exactly the way that I specified in the homework assignment. But if you don't like the look of a ternary operator, you can always turn it into something like this. If n is less than 2, then, well, the curly braces are not technically needed, but I'm going to put those in anyway. So if n is less than 2, then you just return n itself. Otherwise, you return f of n minus 1 plus f of n minus 2. So this program is logically exactly the same as the one in the homework assignment, except this one uses a quote-unquote traditional conditional statement as opposed to a ternary operator. Is that okay? Now, this doesn't mean that you don't have to understand ternary operator, because just because I can translate the homework assignment from ternary operator to a traditional conditional statement doesn't mean that it's going to happen when you go out to work. So when you go out to work, most of the time, you're not writing your new code. You don't get a choice, okay, and say, I prefer, conditional statements over ternary operators. Most of the time, you'll be maintaining code, which means if whoever was before you on that project chose to use ternary operators, you have to understand how to read ternary operators, okay? So in this class, because we are still learning, it's okay. I can translate that for you so that you can see how the ternary operator version is equivalent to the conditional statement version. But you can also see how the conditional statement version is a little bit longer because it is using statements to implement what otherwise could have been done using an expression. So that's basically what it is. So are we good so far with the Fibonacci number homework assignment that's due on Thursday? So are we good? Okay, all right. So what we'll do today, I'm gonna get rid of this now. So what we're gonna do today is to talk about structures, and I think we started on structures before, or haven't we started on structures? We haven't started on structures? Okay, that's fine. Not a problem. So what we're going to do is, I'll give you the C code first, and I'll specify a struct node to look like the following. We'll have, uint 8 underscore t as value, and then we'll also have struct as struct node, and here's a pointer. We'll call this next, okay, without a p in front of it. Technically, it is a pointer, so I should use a p as a prefix, but next is fine. So first of all, if I turn this into a class, does everybody understand what it means? Okay, if I say class node blah blah blah, and then I say everything is public as a public member, do you guys understand what that means? Okay, very good. So a struct is basically a class where everything is public. All the members are public. And if you're using struct in the context of C and not C++, it also means that you cannot have member functions. So you can only have member properties, but not member functions. Is that okay? So it's kind of a very special case of a class. If you understand the class, then this is basically just a special case with a lot more restrictions. So are we good so far? All right. Are there any questions about the struct node part? Okay, next is a pointer to a struct node. Are there any questions about why we can even do that? No questions? All right. So what that means is now we can proceed to our so-called main subroutine. Okay. So in this particular main subroutine, the first thing I'm going to do is to say, let's make an array of a whole bunch of struct nodes. So it becomes, struct node, and I'm going to say this is array A, and it's going to have num nodes. This is the number of nodes within the array. And we'll define that here. Const unsigned num nodes. And, we'll say 5. Or, let's make it 6 this time. Switch things around a little bit. Okay? So right now, main doesn't really do anything. All it does is to have a local variable called A, and A is an array of 6 struct nodes. Is that okay? Okay. All right. And then we're going to do something fun with the array. We'll make a linked list out of all those nodes. So to make a linked list, there are a few ways to do it. The first way is, this is the way I like it. We have a pointer, and then we also have a counter. The counter is nothing more than just an integer, just for counting purposes. Okay, so we'll initialize the counter to the number of nodes. So we have num nodes here, and -1, because the last one is not going to be initialized in this loop. And then we have a while loop. As long as counter is non-zero, we stay in the loop. And the last thing we want to do in the loop is decrementing the counter. By the way, there's no need to copy, everything on the projector because it's all getting recorded. I can double check to make sure that it is all getting recorded, because I would much rather have you guys to pay attention to what I'm saying and try to come up with questions as we go over the concepts. Okay, so what we're going to do in the loop is to say, well, whatever the pointer is pointing to, I have the initialize pointer as well. Whatever struct node is the pointer is pointing to, I want its next member to point to the next struct node in the array. Is that okay? So that means, I have the initialize pointer as well, ptr. So we'll go ahead and do it here. This is the other reason why I don't want you to kind of copy everything in your notes, because I make changes like that. Okay, so it's pretty difficult for you to kind of continuously keep updating your version as well. I mean, when this is all done, you can take a picture. Just take your cell phone and take a picture of that. Okay, so now what we want to do is really just to initialize. Well, we can initialize a few things. Why not? So the first thing we'll initialize is the value member. We'll just make it equal to counter, okay? I mean, that should be possible, right? Is that okay? And then the next thing we'll do, which is the more fun thing that we're going to do here, is the next member is going to be ptr plus 1. This is pointer arithmetic, so I'll explain that later. And the very last thing we're going to do is to say, let's move on to the next item in the array. All right, so up to this point, there's absolutely no assembly coding here. Okay, no architecture, no TTP specific stuff. This is all C, C++ stuff that I'm expecting you guys to understand because it's all coming from cisp310. Now, you may not remember everything, okay, because pointers may be one of the last topic that was only covered in about a week. But guess what? Pointers will come back and haunt you for the rest of your life as long as you program in C and C++. So it's probably a good idea to make sure that we do understand all of these concepts. So we'll start on line 15, okay? Are there any questions about line 15? Line 16. Pointer is initialized to point to the very first, the first struct node of the array A, okay? And then line 17, as long as counter is non-zero, we stay in the loop. And that's matched up with line 22. Every time we go through one iteration, counter is decremented by 1, so eventually we'll get out of the loop. What about 19? Line 19. Are there any questions about line 19? What it is actually doing? We are, well, since there are no questions, then it's
type pointer into node.
Yes.
Okay. So it's putting the data in the node of counter.
No. It's the right-hand side is counter. Counter is just supplying the value that we are using to update something else. But what are we updating? What are we storing? Where are we storing the value into? It's storing into the member value of a struct node that pointer is pointing to.
Right. And so counter is initialized earlier as num nodes -1, so it's
Right.
almost the last element of the array. That's what.
No. A is, but because pointer is initialized to A, so pointer initially points to the very first struct node of the entire array. So the value of the first node in the array gets a value of 5. Okay? But then we want to, so that's what line 19 is going to do in the first iteration. Okay? Is that okay? There's another notation that is equivalent to this pointer notation. So this line could have been done like this. You could have said, I'm dereferencing pointer, which will give you a struct node. Then you can say, of that struct node, I want to change the member called value to counter. So that would have been exactly the same in terms of meaning, even though the syntax is a little bit more cumbersome. Is that okay? So for those of you who are not familiar with the pointer notation, which is dash greater than, you can it's equivalent to first dereferencing the pointer to get the structure, then you use the dot notation to access a member of the structure. Is that okay? All right. All right. What about the next line? The next line looks a little bit more interesting. So what is that doing? Yes.
What if you didn't say PTR plus 1? Does next point to like random, like something random, or is it initialized to null or something?
If I do not initialize, if line 20 does not exist?
Yeah.
Yeah, if line, sorry.
She's wondering what would be in that memory spot if you.
It is uninitialized. Because A, just like the other two local variables, are local variables. So they are not initialized. They pick up whatever is left over, quote unquote, left over on the stack. So the compiler will give you the code to allocate those locations in memory on the stack, but it does not initialize those locations with any specific value until you do that. Okay? So that's important because every single time you use a local variable, in a C or C++ program, you have to remember that in C and C++, there are no such thing as quote-unquote default values in local variables. In most scripting languages, there is a quote-unquote default value, which is known as nil, null, or something like that. You can check, okay, whether a particular variable is just brand new and has no specific value. But in C and C++, they all start with some kind of value. So a pointer has a particular value. We don't know what it is, okay? It can be pointing to location 0. It can be pointing to some other locations. We don't know what it's pointing to. But it's whatever is left over on the stack, okay? Counter is the same thing, okay? Because these lines here, from line 11 to line 13, as far as the compiler is concerned, is really just saying, okay, we got, A that is an array. It needs to take up this many bytes on the stack. We got pointer that's going to take up this many bytes on the stack. We got counter that's going to take up this many bytes on the stack. Add them up and allocate that much stuff to allocate that many bytes on the stack for the local variables. And that's all it's going to do. There's no specific initial values in local variables. So if you do not initialize, like if I miss line 15 or line 16, then counter or pointer will basically just have some kind of random value, and you have no idea what it is. So the program may crash in a particular way one time, and then it can crash in a different way the next time, which makes it really fun to debug. All right. So is that okay? Did that answer the question? Okay, cool. So I'm going to give you an alternative version of what this line actually means. You can also, that will not work with it. No, that's not going to work. Well, it will. Yeah, that worked. It looks superbly confusing, but it will work. It makes more sense? Okay.
It's pretty clear exactly what that is.
Yeah. Yeah, because pointer arithmetics is the plus one is not really just adding 1 to where the pointer is pointing to. It is adding 1, the distance of 1 based on what the pointer is the type the pointer is pointing to. So because pointer is a pointer to a struct node, it is actually adding the entire length of a struct node to pointer when we perform this operation. So that makes it the same thing as what I put in the comments, because it is actually returning the right-hand side is returning the address. If you treat pointer as the beginning of an array, it is returning the second element, the address of the second element of that array. And this is one really cool thing that C and C++ can do, is you can take any pointers and treat it as if it is an array. But this is also why it is not so fun when you access that array out of bound. There are no programming languages that I know of, okay, other than C and C++, that allows you to play with pointers the way that you can in that particular language, which gives you a lot of power, gives you a lot of things that you would otherwise not possible to do. But if you do not respect the end of an array and access something out of the end of the array, it can give you problems to no end. So just kind of keep that in mind. All right, so next name is pointer plus PTR. So this is really the same thing as PTR equals to the address of, treating PTR as an array, but the second element of that array. Okay, it's kind of the same thing like that. Is that okay? All right, and I don't think line 22 is going to present a challenge. So that's basically how we initialize the first num node minus 1 elements in the array. So that leaves the last one uninitialized. So with the last one, we're going to do something here. So we'll say by the time we get out of the loop, pointer will be pointing to the very last element of the entire array. So with the last one, we'll say the value is, I don't know, FF, okay, 255. And then we'll make the pointer to go to 0, to basically indicate this is the end of the linked list. Do not follow this pointer any further. Is that okay? So this will give you a linked list, okay, what we know as a linked list in CISP 430. All right. Sorry? Yes. So NULL, all uppercase, null, is basically just 0. Yeah. The constant 0, as it is like this, just the digit 0 by itself, is very special because you can assign 0 to a pointer type without casting, and the compiler won't give you any, griefs. So it can be automatically casted even to pointers. You cannot do it with like 5, okay? Try to assign the constant 5 to a pointer type, your compiler will bark, okay? But you assign a 0 to a pointer type, it's all good. So 0 is very special because can be used as a Boolean, as an integer, can automatically cast into a double, okay? But it can also be automatically cast into a pointer. So that's why, 0 is kind of special. So are we good so far with the initialization of the array? Okay. Does anyone want to look at the picture of, how these struct nodes would look like? Kinda? Okay. So let's go ahead and do that. There's a chirping sound from somewhere. All right, so let's see. Do I have Zerno still up? Yep, I do. Right here. And then we'll start with a new one. Discard the other one. There we go. Okay, so what we have here is initially we have A, and array A is an array of a bunch of struct nodes, 6 of them to be exact. So we have 6 individual things, and those are the struct nodes. Okay, so if I want to write the index, this is for the index 0, 1, 2, 3, 4, and 5. That's the last one. Each struct node has 2 individual members. The first member is V, and the way I'm going to initialize it is this is going to have the first V is going to value has a value of 5. The next one is going to be 4, 3, 2, 1, and this one is going to be 255. Okay, it's 255. Okay. But what is more interesting is what's going to happen to the second member of each structure. The second member of the structure, which is next, is going to be the address of whatever the next struct node is in the array. So that means if I use an arrow to indicate the pointers, so that means this thing is going to point to here, this thing is going to point to here, this one is going to point to here. It just keeps pointing to the next item. Did I make a mistake here? No, that's just a 1. Okay. And then this one points here. But this one, I'm going to use the ground symbol to indicate that this is the end of the list. It has a null value to indicate that, well, don't follow this pointer any further. It is not a valid value. It has a null value. Is everybody familiar with a null pointer? Where it basically indicates do not follow this, right? It just says this pointer points to nowhere. Is that okay? So after the initialization, this is what we're looking at, which is also known as a linked list. So if you get a handle on the address of the first node in the entire array, even without indexing, you can now follow through the rest. Okay, so this is a linear linked list in CISP 430.
Or
singly linked list, yes. It's a singly linked list because it doesn't have a pointer going back. Then it becomes a doubly linked list. It's also non-circular. Because in some cases, you can have the last pointer to point back into the first one, so it becomes a circular singly linked list. Sorry? Yes. Yep. So do we have any questions about what the code is going to construct? Is that okay? Yep.
Why is there 255 there instead of 0?
I'm just choosing to use a 255 at the end of the array. Could have used a 0. It doesn't really matter. As long as we know what it is going to be, it's fine. Because then we can check whether it got it done correctly or not. Okay? So any other questions about what we are trying to do to the array? Is that okay so far? But this picture is also important in the sense of, we know exactly how the bytes are going to be used in memory. So the very first byte of the entire array belongs to member value of the first element in the entire thing, which is a part of the struct node. The second byte is the second member called next of the first struct node of the array. The third byte is going to be the value member again, but of the second struct node of the entire array. The fourth byte is going to be the next member of the second struct node of the array, and so on. So this picture also serves the purpose of showing you how memory is going to be used in the toy processor. Are we doing okay so far with this? Okay. So now, if I look at just a struct node by itself, okay. Oops, didn't mean to switch. So if we look at the struct node by itself, okay, and my convention is this is low memory and that's high memory. A struct node only has 2 bytes, pretty easy. If you know the beginning of the entire structure, that is also the beginning of the member value. But if you add 1 to the beginning of the entire structure, then you get to the address of next. So this is a pointer to the structure itself. Is that okay so far? I mean, it's just really looking at a struct node up here, but sideways, right? So if you look at this new picture of a struct node sideways like this, if you rotate your head counterclockwise 90 degrees, then it will look like that. Is that okay? Don't twist your neck though. We're not owls. Can't really turn our necks the same way. Is that okay so far? All right. Okay, so this is cool. So now we can switch back to the code here. And now we really start to think about how do we implement this in assembly? Well, first of all, I'm not going to compile this program and run it in C. We can do that later on, okay, if we have time. But the focus is to look at this code and say, well, how do we translate this into assembly? So we'll go ahead and start a new, not a new document, but a new window. So this way I can show you the assembly code and the C code side by side. I'm going to cover over some of the comments because the comments really doesn't serve any purpose other than telling you, what other way can we specify exactly the same thing. The first thing is, well, how do we represent a structure in assembly? And the answer is, it cannot natively do that. Okay, it's not in the vocabulary in an assembler to represent a structure. And then you guys might think, well, that's only because you use a spreadsheet to implement an assembler. What about real assemblers that people use in industry? Same thing. And no assembler that I know of natively understands the concept of a class or a structure. That is simply a high-level programming language construct that no assembler understands. Okay, great. Then what are we going to do about this? Well, we have constants. We have labels. So we can utilize labels to help us with that. So I'm going to say node underscore value to represent the offset in number of bytes from the beginning of a structure of type node to the member called value. Is that okay? What do you think that's going to be? Let me say that one more time. So node underscore value is a label, it's a symbolic name, representing the number of bytes from the beginning of a struct node to the member value of that struct node. What do you think that offset is going to be? 0. It's the first member. Okay, the first member of a structure has the same address as the structure itself. Does that make sense? Okay. So that means, okay, it's just a constant of 0. What about the next one? Okay, it's called next. What do you think? Where do you think we can find the next member, the second member of this particular structure with the name of next? If I know the beginning of the structure, what is the offset to find next as a member? It's 1 byte off. Okay, cool. So now we can say, now we can do this, okay? But we can also do better. Yep.
It is necessary to put 0 after the label of your first.
Yes, because without the 0, then it's defined to the current location in when you assemble a program. If you put this all the way at the beginning, yeah, then it's the same thing as 0. But if you put it elsewhere, then the label node value would be off.
Did you say a couple lectures ago that that's initializing stack pointer?
That's a separate thing. We are defining labels right now. So the way I define these labels can go anywhere in the program. It will still work exactly the same way, which is the whole point of doing it, giving it an explicit 0. Okay. And then we also want to know what is the size of a struct node. Well, that's not too bad, because all we need to do is to say, what is the last member, or what is the offset to the last member of the structure? Let's add the size of that last member to the offset of the last member. Then it becomes the size of the entire struct node. So this is a fancy way to say that each struct node uses 2 bytes. But the way I specify it using references to other labels also means that if you really want to add additional members to the structure, it becomes pretty easy to maintain the relative relationships between the offsets and the size. Okay, and that's why I avoid the use of constants except for the very first one. Everything else is only relative. Is that okay? All right, so that takes care of how a quote-unquote structure is defined here. And then we have a const unsigned integer, num nodes. Well, we can just use a label to represent that as well. Okay. So that takes care of lines 1 to 7 of the C program in assembly. So the structure is not really represented as a structure, but it is now represented by a whole bunch of labels that represent, 2 of those represent offsets to individual members inside the structure, and then one of them is representing the size of the whole structure, which can come in handy later. Is that good so far? Okay. So now we have to specify the actual code in main. Before main, we have to initialize the stack pointer. Okay, this is the usual typical stuff that we do. And then we have main technically starting here. And then the first thing we have to do is to allocate for a whole bunch of stuff on the stack. Okay. We have to first allocate for array A, then we have to allocate for the pointer, then we have to allocate for the counter. Okay, we'll do one thing at a time, okay? Now, in a compiler, it will just add up everything and then do one single allocation, but instead of doing that, let's go ahead and do it kind of gradually, okay, step by step. The first thing we need to allocate is for the entire array A. How are we going to do it? First of all, how many bytes is it going to take up? It will be num nodes times node underscore size, right? That's going to be the number of bytes we need for array A. Is that okay? So what we'll do is we're going to say LDI A, okay? And then we have that expression. The expression is num nodes, and then we have node underscore size times postfix notation. So that would be the product of num nodes, which is the number of struct nodes in the array, times and node size, which is how many bytes each struct node is going to take up in the array. So the product is going to be the total number of bytes used by the array. Is that okay? Then we will do the allocation here. So we're going to say subtract this much from the stack pointer. So we'll just say allocate for array A here. Is that okay? And then we have a pointer. Well, pointer is easy. Decrement D. Allocate for PTR. And then counter is pretty easy too. Allocate for counter, because pointer only takes up 1 byte and counter also only takes up 1 byte. Okay. So when this is all done, the stack pointer is pointing to what? No. Counter, yes. So by the time this is all done, the stack pointer is pointing to counter. Okay. So I'm going to use a whole bunch of symbolic names to help me remember the offset of each local variable from where the stack pointer is pointing to. So the offset to counter is 0, because that's the last thing that we allocated on the stack. And then we have pointer, which is counter 1 plus. And then we have array A, which is pointer 1 plus. Is that okay? So I'm using symbolic names to help me remember which local variable is how many bytes away from where the stack pointer is pointing to. So this way I don't have to keep track of all of that in my mind. Okay? I just use the symbolic names to refer to the local variables. So it's a pretty useful trick. Okay? If you're writing multiple subroutines and stuff like that, you can probably prefix each one of these with the name of the subroutine. So this way, if subroutine main has a counter and subroutine sort has a counter as well, then it becomes main underscore counter and sort underscore counter. So they can be differentiated. But since I only have one single subroutine, I'm not doing that. Okay. So now, what are we going to do with the initializations? Num node at -1, it needs to go into counter. That's pretty easy. Now, if you say, I don't want any shortcuts, I just want to know the mechanical way to do it, this is the mechanical way. You use LDI to load the offset to a particular local variable into a register, A, B, or C, pick one. Okay, like that. And then you add to that particular register the stack pointer. That will compute the address of the local variable that you want to access. Does that make sense? Because the counter as a label is denoting the number of bytes that the local variable is away from where the stack pointer is pointing to. So if you add counter as the value of counter to the current value of the stack pointer, that will give you the address of counter, but not the content. Which is fine. Huh? So I'm implementing line 15 right now. Yeah, only 15 because I need to initialize counter first. Okay, so this is the left-hand side. Okay, the left-hand side is counter. The right-hand side is pretty easy too, because it's just num nodes -1. So because num nodes is a label, so I can actually do that. So this basically is the postfix version of num nodes -1. So now you can see how useful being able to express postfix expression is in an assembler. I know you guys are thinking, but infix would be even better. Yes, I know. But infix is much harder to parse, and I'm lazy. So postfix it is. Well, besides having some exposure to postfix is not going to kill you. It might even help you in your career. It might. If it doesn't help you, don't come back to me and say, I want my money back. Okay, so there we go. We just store, num nodes -1, which is in register B, to where A is pointing to. But where is A pointing to? A is the address of counter. So this initializes counter to num nodes minus 1. Okay, line 15 of the C code, done. All right, so we'll take a look at the second line, which is line 16. Line 16 is a little bit more cumbersome because the first thing we need to do is to compute the address of the array A. But that's about the same thing. You load A with A. Now this time it is kind of confusing. The second A is a label. The assembler automatically knows that because by context, it knows that the second A cannot possibly be a register. Okay? So to the assembler, there's no confusion, but to us, it can potentially be confusing. So then we use the same technique, add AD, so that register A, I'm going to make it very clear, register A is now the address of array A. Okay? Yep. You can change it to a B, sure. Or a C.
On line 24, you said AAD instead of AD.
Line 24.
You spelled add incorrectly.
Oh, add. Okay. There we go. Okay. Couldn't spell today. I wonder how AAD is going to be pronounced. Yep, question?
This is in the C code that you meant to also type in, right?
Where?
In the struct of C, in the C code for struct.
In the C code for struct?
Is that supposed to be units or unsigned int? Never mind. Unsigned int.
Yep, unsigned 8-bit integer. Yep. Okay, so this is the right hand side of line 16, and then we have to now deal with the line because the right hand side only needs the address of the array. We don't need the content of the array, so we are done with the right hand side. The left hand side is kind of the same deal. We just cannot use register A again. So now we will load register B with PTR, the label, and then we add BD. So at this point, register B is the address of the pointer. And that's perfect because that's what we need in order to store something to the local variable pointer. So now we have a STBA so that PTR equals the address of A is done. So now we got line 16 done in C. Any questions? We good? Okay. Now we move on to line 17. Now the way I do line 17 means you probably don't want to write it down or copy it by hand. And I'm going to move the editor up a little bit because I think people in the back of the classroom may not be seeing this very well. So I'm going to move this up a little bit. And then the same thing with the other editor. There we go. All right. So now we want to implement the loop. So the way that I usually implement a loop in assembly is I just put in the skeletal structure first. So I have while begin as a label, while end as a label, and then right before the while end, I have an unconditional branch back to while begin. So this is kind of like the really bare minimum skeletal structure of a loop. Then I work on the condition so that I know when I'm supposed to get out of the loop. So in this case, the condition to get out of the loop is as long as counter is non-zero. So I have to get to the value of counter to figure out whether I should exit or not. Same thing, LDIA with counter. Yeah, this keyboard is kind of bouncy. I double tap a lot of times. I don't know why. Add AD. So now register A is the address of counter, which is not what I want to use for the comparison. I need to do one dereference to get to the value of counter. So I'll just do this. So that A is now the actual value of counter, not the address of counter. And then we can use the old trick of AND AA, okay? Instead of comparing to 0, which is kind of cumbersome, I just use the trick of AND AA. Basically, all this is going to do is to force register A through the ALU, and therefore setting the Z and also the sign flag. I don't use the sign flag at all, but the Z flag is really useful because the Z flag tells me whether it's 0 or not, okay? And then we do a JZI, which is the only instruction that can make use of the Z flag. So if the Z flag is set, that means whatever is going through the ALU is a 0. Okay, whatever is coming out of the ALU is a 0. So, oh, well, that means we should get out of the loop. Let's go to while end. Okay. So this is the actual beginning of the body of the loop. Line 36 in the assembly side, on the assembly side. Are we good so far? So this is why I said, don't hand copy the code because, I keep inserting things in between stuff. Yep.
So in the very beginning, or the condition of our while, we're again loading another thing into register A.
Yeah.
But the last thing that was in register A was the stack. Actually, I'm sorry, we had something in register A.
Yeah.
So
that's going to override it.
It's just going to override it. We don't
Yep.
need to worry about deallocating.
No. Yeah, when it comes to registers, there's no allocating nor deallocating. Registers are basically, there are 4 little scratch pads that you have access to, but as soon as you load a new value into one register, whatever value that it had earlier is gone. Okay? So are we good so far with the assembly code? Okay? So we are reusing register A, B, and C, basically on a per statement basis in C. So now we get to line 19. Line 19 looks kind of ugly, but it's not really too bad. For one, register A, or the value of counter, is really in register A already. But can we count on that? Yes, we can. So that's kind of handy if you don't want to blindly just compute the value of counter and put it into register A. But on the other hand, if you say, I don't want to take any shortcuts, I don't want to have to read code before the implementation of line 19 in C to know that register A does have the value of counter, then we can just reload it, okay? It's not that big of a deal. So we'll just repeat those instructions here. LDI A counter, add AD, and then LD A. So now A is counter. Okay, I know it's redundant, but it doesn't hurt to basically say this is how we compute the right-hand side, which is not the difficult part, right? The difficult part is the left-hand side. How do I store something to member value of the structure pointed to by pointer? Maybe I need the address of that thing first, right? Because in order to store to something, well, you need to know the address. So now the question is, what is the address of member value of the structure pointed to by pointer, PTR? Don't you think we need to figure out what pointer is first? Okay, so let's do that. Let's figure out what is the value of pointer, the local variable. Same thing, cannot use register A, but we can use register B. Okay, and so that will make B the address of pointer, which is not what I want, because I want the pointer itself. I don't want the address of the pointer, I want the pointer. Okay. Do we want to dereference right now? Nope, because if we dereference right now, we'll be looking at the first byte of the structure, which may or may not be the member that we want to access. Okay, so what we want to do now is to do something like that. So we load another register, let's say C, with node underscore and then the name of the member, because node underscore value as a label is telling me how many bytes the member value is away from the beginning of the entire structure, right? But I do know where the structure is because register B is pointer, which is pointing to the beginning of the structure. So on one hand, in register B, we know where the entire structure is, and then on register C, we know how many bytes value as a member is away from the beginning of the entire structure. How do I get to the address of member value of that structure? Add the two registers, okay? So we just add them together, and which way you add is going to be okay. Either way is fine because both of these are scratch registers. So I'm just adding C to B. Okay, so at this point, B is the address. Okay, so I'll make it very clear. So at this point, B is the address of member value of the structure pointed to by pointer. So if this is not entirely clear to you, then what you want to do is to review the material after class. Okay, you can watch the video after class. Pause right here, and then draw a picture of how what each register is pointing to, and how the registers change the value. So that register B, which initially was pointing to the beginning of the entire structure, is now pointing to a particular member of that structure. And then one of you is going to say, oh, but I remember node value is a 0, so why do we bother to add a 0 to something when it is useless? Well, it's because what if I later on decide to insert a new member into the structure before value? The value is not 0 anymore, because I don't want to remember to have to come back here and change this code because I decided to insert another member before value. So this makes it universally useful. Okay, I can keep changing the ordering of members within the structure, and it wouldn't impact my actual assembly code because I used the most general version of the code that is independent to how I want to define the ordering within the structure itself. Is that okay? All right. So it does use up a little bit of execution time, but it's a small price to pay when I gain flexibility of altering the structure later on without having to impact this code over and over again. All right, well, this is good because register A has the right-hand side, and then register B has the address of the left-hand side. So now we just have to, do a store. We're done. That's for line 19 of the C code. So lines 36 to line 44 of the assembly code is what we use to implement line 19 of the C code. Is that good? With a cisp architecture, it can potentially be done in fewer lines of code, but this really illustrates how we do all the computations. There's nothing hidden in this particular case. All right, getting on to line 20 in the C code. It's about the same kind of deal, except the right-hand side is computed a little bit differently. So we need to get to pointer first. Okay, so we'll do a LDI a pointer, add AD. So now we get the address of pointer. We do 1D reference, LDAA. So the A is now pointer itself. And then we do the increment. Okay? Wait, do we just do an increment like this? No, because that add one, that plus one, is type dependent. It depends on the size of the things that pointer can point to. I mean, pointer is not a uint8 pointer, is it? It points to a structure, so we should add the size of the structure to register A. Is that okay? Because we're trying to calculate the address of the struct node, the next struct node. Pointer points to a particular struct node, but we want the address of the next struct node. So the number of bytes in between is represented by the label node underscore size. That's one of the reasons why we have to have that label. Okay, well, that's not too bad. We just do a LDI B, choose another register, node size, and then add those two. So that is okay. So now A is, in C syntax, pointer plus 1. So now we got the right-hand side. Register A has the right-hand side. Left-hand side is kind of the same thing that we did before, except this time we're accessing next as a member instead of value as a member. So it's going to be pretty much about the same code as last time. So we have LDI B with pointer. I know I could have saved some code if I use the registers more carefully, but that's okay, because this is how mechanically a compiler would do it. So I'm just resembling, how a compiler would do it, kind of mechanically. Okay. LD, cannot use A, so we got to use B. So LD B. So B is now pointer, the value of the pointer. And then we have to do LDI C with the offset to next, which is under node underscore next. And we add BC, so that now B is the address of member next of the structure pointed to by pointer. So now we can just do a store instruction, stb, what was it again? A is the right hand side. And now we are done with line 20 of the C code. So are we good so far? Are you guys starting to see a pattern? Like, oh, so there are a particular sequence of code that we keep seeing over and over and over again. Okay? All right. Line 21. What do you think we should do with line 21? If we already know how to do line 20, don't you think line 21 is not that big of a deal? Because we know how to calculate pointer plus 1. We just have to store that value back into pointer. Into pointer as a local variable on the stack. Okay? So the registers are only useful within a statement in C, but across statements we try not to reuse registers. Now a compiler, if you turn on optimization of a compiler, it will try its best to reuse values already calculated in registers. But that is not something that we are going to do here, because we are just trying to figure out mechanically how to implement each construct. So we're not going to add on top of that, optimization concepts. Okay. All right. So let's do this. So we'll go ahead and redo the whole thing. Okay. Load A with pointer, add AD. Okay. So now register A is the address of pointer. But this time, I'm not going to overwrite register A with pointer itself. So when I use the LD instruction, I'm going to use a different register. So the B is now pointer. The reason why I'm doing this is because I also need to use yet another register C with so that I can load it with node size, so that I can compute pointer plus 1. So when I add BC, then B is now pointer plus 1. I need to store that thing back into pointer. That's good, because register A still has the address of pointer. So a st instruction to whatever A is pointing to, which turns out to be pointer, the local variable, with B, is going to accomplish what we need to do with P++ pointer. Because plus pointer is really the same thing as pointer gets pointer plus 1. Okay? So are we okay so far in terms of the assembly code implementation of the C code? Yep.
Wasn't on line 50A already pointer plus 1? So like
Oh, but we have since used change A many times. Yes. So on line 50, register A is pointer plus 1, but look, we just overrode it with stuff.
Oh, okay. No, that's what I was saying, because like you're doing the same. So you're storing from line 58, you're doing the line 21 of the C code, right?
Yes.
Yeah. So like since it is already pointer plus 1, can you store that A?
Oh, I see.
Just use A.
So we can still use register A. Remember what I said a little bit earlier? We're not optimizing the use of registers across statements in C, because that would make it kind of difficult to read, because it requires you to keep track of what each register has across statements in C. So that way, it's much more difficult to debug a program that way, because now you can no longer say, oh, there's a locality to how a register is used. I only have to focus on how registers are being utilized within the implementation of one single statement. Now you have to remember, oh, what was in register A when we get to here? Oh, that's right. Okay, it has got pointer plus 1. Right. Right. So the resulting code is not optimal, obviously, because we're reloading stuff in and out, but from the perspective of, can we look at just a small chunk of code and understand what it is implementing? It becomes a lot easier. Because in this case, line 21 is really just implemented by line 58 to 63 on the assembly side. There's nothing else that you need to rely on to get to that part. So I think for instruction purposes, this is better. In terms of execution time, yeah, it's a little bit wasteful. I mean, it's not too bad. Okay. So now we get to line 22 of the C code. We're almost done. Pretty close. All right. And I think we got enough time to test the code. Okay. So line 22, kind of easy stuff. We just load A with counter, add AD. So now register A is the address of counter. And then we load B with A, so that B is the value of counter. This time the decrement is really just decrementing by 1, because counter is just an integer. So we just say decrement B. So the B is now counter minus 1. And then we want to store that back into counter. And fortunately, register A is still pointing to counter. So STAB is going to finish the operation. So now this is how we decrement the counter, which is the last thing that we need to do in the array, in the loop. So now after the loop, we still got a few things to do. We have to store a FF into member value of what the pointer is pointing to. So at this point, I think we can go a little bit faster. Well, okay, 0xff, which is 255, LDIB with pointer, and then add BD, and then we have a LD BB, and then we LDIC with node underscore value, add BC, STBA, and we're done. That's line 24. And if we know how to do line 24, do you think we can do line 25? Kind of the same thing, just switch things over a little bit. So LDI A with 0, LDI B with pointer, add BD, load BB, LDI C with node underscore next, add BC, and then STBA, and that's the entire program. Cool. But wait, there's more. At the end of this entire program, we have to deallocate everything on the stack, right? So how do we know how many bytes is now allocated on the stack? There are 12 bytes just for the array A, right? And then there's 1 byte for pointer, and then there's 1 more byte for counter. So if I want to know the total number of bytes used so far in this case, then I'm going to load it with another register, let's say register C, and then we can do the calculation, right? So we can say, okay, how many nodes do we have? Num nodes. How many bytes does each node use? Node underscore size. Let's multiply those. Oh, but wait, there's 1 more byte used by counter, and then 1 more byte used by pointer. So that becomes the total number of bytes used on the stack by local variables. Okay? So the first part here, calculates the total number of bytes used by the array, add 1 byte used by counter, add 1 more byte used by pointer, and then we should have 14. Is that okay? Yeah, I'm not done yet. Okay, this is just calculating the number of bytes I want to deallocate. Okay, so register C has the number of bytes that I want to deallocate. So the deallocation is really just adding that many bytes to the stack pointer. Yep. So the usual way to deallocate is byte by byte is increment. But since I don't really need to deallocate byte by byte in this case, I just say, oh, okay, there goes 14 bytes. I don't need those 14 bytes anymore on the stack. So I just move the stack pointer up by 14, and we're done. So now we are ready for the halt instruction to end the entire program. All right. So are there any questions about the concept? Yep, go ahead.
I think back on line 58.
58?
Yes, 58.
Let me scroll back. 58.
I think it's our first statement.
Line 58 is we're accessing pointer. Okay, so this is a good exercise of disassembling. So we'll figure out what it does, right? So by this time, A is the address of pointer, B is now pointer itself. I'm adding node size to pointer to get to the next location, and then I'm storing that back to what register A is pointing to, which turns out to be pointer. So line 58 to 63 is implementing line 21 of the C code.
So I think, if you were to just go there, I'm a little lost as to where we are in our linked list.
So
Or it's not.
it's moving on to the next structure to initialize the next structure. Yeah.
Because we haven't ran anything, so technically we're just setting it up.
We are just setting up the linked list, correct. Yep. So are there any questions about the setup? The implementation of the C code, the concepts involved? Okay. If there are no questions, we'll go ahead and assemble and try to run this code and see if I'm going to embarrass myself because it doesn't work. That's always that off chance, right? In my case, it's not going to be that off. Sometimes I get excited when the program doesn't work because then it becomes a mystery. It's like, I wonder why is it not working? Okay, cool, let's figure it out.
Did ever in your life it used to be frustration?
Not because of programming. Oh, wait, I need to assemble first. So let's go find my browser. Okay, here's my browser. Do I have the assembler up? Yep. Okay. And the source code from yesterday is about the same. Okay, so we got about the same kind of code here. May not be exactly the same, because I can do two things, do the same thing twice on consecutive days, and it will be different. All right. So we don't have any errors. Excellent. So we'll file, download as CSV, and we'll call it linked list. .csv. Switch back here. Load the entire image. Link list. .csv. All right. So I have, I would say about 70% confidence that this is going to work. So I'm just going to do a Control K. Okay. So it has reached the pause, the halt instruction. Control K to stop again. So the first thing I'm going to check is to see whether the stack pointer is balanced. So we go to the register bank, look at register D. It's balanced. Okay, so that's a good sign. And then we're going to go into the memory here and say, can we see the the remaining of what we worked on earlier? Okay, so we can see the memory map here. Do we know which portion is what in this particular case? Well, we should be able to tell, right? Because the last portion is the array A, and it takes up 12 bytes. So we now say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So from here on, that's my array. We know that each struct node takes up 2 bytes. So these two is the first struct node. These two is the second, third, fourth, fifth, and this is the last. Okay? Do they have the correct values? In other words, the first member, the first byte is the first member, which is value. So they are supposed to go from 5, 4, 3, 2, 1, and then for whatever strange reason, I decided the last one should have FF, or 255. So that part worked out. Are they pointing to each other? Is the next pointing to the struct node following the one that we're referring to? Let's find out. F6, is F6 referring to this location? Is F8 referring to this location? FA is referring to this location. FC is referring to this location. And then we have FE referring to this location. The last one has a null pointer, which is 0, 0. So everything seemed to work. What about pointer and counter? Because if we can check the array itself, we should be able to double check pointer and counter to make sure that they are also with the correct value. So this is our pointer, PTR. It's pointing to the very last struct node of the entire array. Is that correct? Is that where it's supposed to be pointing to?
How do you know again if it's pointing to the correct place? I see.
Because it has a value of FE.
Okay.
So the last location is FF. This thing has a location of FE. So it is supposed to be pointing to the very last thing. So that would make this 0, 0 counter. Is counter supposed to be 0, 0 at this point? We're at the end of the entire program, we got out of the loop. The only way to get out of the loop is when counter becomes 0. So the counter being 0, by the time we hit the halt instruction, is also correct. So as far as I can see, based on the memory trace left by the program, it seemed to work correctly. Is that okay? So this is kind of how we can use assembly to even get into, well, I would say very simple data structures. Are there any questions about the C code? So let me switch back to the C code and the assembly code. Okay, here's the assembly code, and here's the C code. Are there any questions? Because I just want to scroll this to kind of the trickier part of the program and the implementation. So here's a question, okay? Remember what I said? What if I want to change the structure up a little bit, get more stuff in it or change the ordering of things, right? So what if I change it so that, okay, I'm just going to exchange these two and then add something in between. So we'll have u in 8 underscore t. This is extra value, okay? What are we going to do in the assembly code? Well, let's see. We go to the assembly code, and then we say we have one more thing, okay? So node next is now defined to be 0. And then we have node underscore extra value being node next 1 plus. Okay, and then value is now node extra value 1 plus. Get rid of this here, and then node size is going to be node value 1 plus. By rearranging or redefining the labels like this, the rest of the program will now function the way it's supposed to. I don't have to change anything in the rest of the program because I did not make any assumptions. I did not optimize and go, oh, since node underscore value is 0, let's not add it. I added it anyway. But because of that, I don't have to adjust anything else. What about the size of the program? Now the array is going to be bigger. When we do the pointer plus 1, it's going to have to add 3 bytes instead of 2. It's all taken care of because of the use of symbolic names. So that's what makes it kind of really cool. So before we end today's lecture, there's one more thing. What is the whole point of implementing structures in assembly code? Because isn't that the whole point of using C and C++? Right? So what is the whole point? I don't see that at all. Okay. So let's go check out my website again, arccis.net. And this time we'll go to the root part here. There we go. So we'll go to, not teachers, develops. There we go. So these are all the things that I have done in the past. Some are really, really a long time ago. But I wrote a real-time kernel at one point. And the real-time kernel itself was written entirely in assembly code. This is the same architecture as the one used in Arduinos. So it's not some random architecture that tech invented. This is real, okay? But the real-time kernel, even though it was written entirely in assembly code, when you need to use it, the API is actually C compatible. In other words, if you want to add a new thread to the real-time kernel, it's a multi-threading kernel, this is the API. You just write you access the real-time kernel using regular C code. This is the reason why it is important to understand how structures in C are actually how it works, so that you can write assembly code that can be called from C to get something done that otherwise cannot be implemented in C. You cannot write a real-time kernel in C. You just don't have access to the resources that you need access to when you're writing something in C. You have to do it in at least partially assembly code. So, but the big question is, when you write that code in assembly, how do you make sure that it is callable from C and it understands, higher level constructs that you can only see in C programming? This is the reason why it is important to understand how structures work in assembly code. Do you think it's important to have a real-time kernel, on one of those things? It gives you the ability to have multiple threads. You can actually have your Arduino to perform multiple parallel tasks at exactly the same time. That would be kind of cool. I mean, for those of you who went to debugging bee or with some background in programming the Arduino, you can have one thread that is only responsible for motion control, one only responsible to deal with the sensors, one only responsible to use Bluetooth to communicate with an end user. They can all be running separately and independently until they have to rely on each other. Then we have semaphores and other things, to kind of synchronize between the threads and do all kinds of fun stuff. So are we good so far? I just want to explain the rationale because, I don't want you guys to think, yeah, who's going to do that? Okay. So now at least you know who. Whom, I should say. All right, so we'll go to the lab. There's no new lab activity, so it really is the same thing. We just have the swap subroutine and also Fibonacci to finish up.